In this video, we're going to learn about discrete and continuous probabilities. Discrete and continuous random variables. A variable is a quantity whose value changes. Discrete variable is a variable whose value is obtained by counting. So we have the examples, the number of students present, the number of red marbles in a jar, the number of heads when flipping 3 coins, students' grade level, and we have continuous variable, a variable whose value is obtained by measuring. So we have an example as height of students in class, followed by weight of students in class, time it takes to get to school, distance traveled between classes. A random variable is a variable whose value is a numerical outcome of a random phenomenon. A random variable is denoted with a capital letter. The probability distribution of a random variable x tells what the possible value of x are and how probabilities are assigned to those values. A random variable can be discrete or continuous. A discrete random variable x has a countable number of possible values. As you can see here on this example, our x now is in representation of real numbers, whereas each real number has their respective probability. To graph the probability distribution of discrete random variable, construct a probability histogram. As you can see here, whatever real numbers of x listed above is plotted on the x-axis, whereas p of x, okay, this is actually y variable, or the probability of x is in occurrence in this axis. A continuous random variable x takes all values in a given interval of numbers. The probability distribution of a continuous random variable is shown by a density curve. The probability that x is between an interval of numbers is the area under the density curve between the interval endpoints. The probability that a continuous random variable x is exactly equal to a number is 0. Again, the probability that a continuous random variable x is exactly equal to a number is 0. The mean of a discrete random variable x is its weighted average. Its value of x is weighted by its probability. To find the mean of x, multiply each value of x by its probability, then add all the products. The mean of a random variable x is called the expected value of x. Now we have this formula of mu x, or the mean, is equal to the summation of xi and their corresponding probabilities. The law of large number. As the number of observation increases, the mean of the observed value, x bar, approaches the mean of population, mu. The more variation in outcomes, the more trials are needed to ensure that the mean is close to the mean of the population. So we have the rules for means, as if x is a random variable and a and b are fixed values, then if x and y are random variables, okay, we have these formulas: mu of a plus b of x is equal to a plus b multiplied with the population mean for variable x. The other one, if it is represented by x and y random variable, mu of x plus y, or the population mean of the sum of x plus y, is equal to the population mean at x and population mean at y. If x is a discrete random variable with mean mu, then the variance of x is we are given with this formula as sigma of x squared is equal to the summation of this quantity, individual element of x minus the mean population of x squared multiplied with the probability. This standard deviation, sigma x, is the square root of the variance. So we have rules for variances. If x is a random variable and a and b are fixed numbers, then we have this one as the variance, okay, sigma of a plus b of x, or the standard deviation of a plus b of x squared is equal to b squared multiplied with the variance of x, or the standard deviation of x squared. If x and y are independent random variable, then we have these following relationships. The sum of x and y, we're going to use this one. And the difference of x and y, we're going to use this one. Okay. So we have these same formulas. The variance, sigma squared, of a discrete random variable x is the number as this one. Variance, or standard deviation squared, is equal to this relationship as discussed earlier as the summation of x minus the mean population squared multiplied with the probability, which by algebra is equivalent to the formula of this. If we're going to distribute the probability, or P of x, to each individual elements, we came up with this. The standard deviation, sigma, of a discrete random variable x is the square root of its variance. Okay? So if we get the square of this, we come up with this value as standard deviation is equal to the square root of summation of this quantity as x minus population mean squared multiplied with the respective probability. Or if we're going to distribute this or simplify this algebraically, we get this value. Let's proceed with continuous probability. So this one differs with discrete probability. X is said to be a continuous random variable if there exists a function f of x associated with x called the probability density function, with the properties of f of x is greater than or equal to 0 for all values of x. Now, if we're going to express this in calculus, okay, f of x derivative of x, we're going to set our limits now, whatever values we got, with our lower limits as the negative infinity up to its upper limit infinity, okay? These quantities must be equal to 1. All summation of values of probability must be equal to 1. Now, probability, whereas if x lies between a and b, we're going to use this relationship as f of x, d of x. We're going to set now your lower limit at a to an upper limit of b. This gives us a function of b minus function of a. So the second key point for a continuous probability, let x be a continuous random variable with associated PDF. PDF stands for probability density function. F of x, then its expectation and variance denoted by E of x. Okay? When we say E of x, that is expected value. Or mu. For continuous probability, expected value is equal to the mean population. And V of x, okay, this is actually your variance. For continuous probability, variance is represented as V of x or the function of x, okay, respectively are given with this following mathematical representation. Whereas if we're going to equate now your mean population to expected value, this gives us with the following limits, okay? We're going to use this formula as if we're going to set now our limits, since we are not given with any values, our limits now is negative infinity to infinity, okay, of x multiplied with whatever function given times the derivative of the whole function. Whereas solving now for variance, v of x or sigma squared, okay, is equal to this following formula as x minus the mean population quantity squared multiplied with a given function of f of x, and then you're going to get to derive it as d of x. After that, we're going to get the integral process or integral equivalent of this whole function. Now, algebraically distributing f of x to x minus mean population squared, this gives us with this relationship. So if we have a quantity probability for a discrete variable, it is represented as P of capital X would be equal to small letter of x. For a continuous one, f of x dx. For allowed values, discrete variable is limited to this one. P of x is equal to x, which is greater than equal to 0. Whereas for a continuous variable, f of x must be greater than equal to 0 as well. For this summation, okay, we have sigma of the probability of x would be equal to x, whereas for a continuous variable, this is equal to the integral of f of x dx. For expected variable under this discrete variable, e of x is equal to the summation of x multiplied with the probability of x such that it is equal to the x. So we don't have a definite form for a continuous variable. For a variance, v of x is equal to sigma or summation of this following quantity as x minus your mean population quantity squared multiplied with the probability of x be equal to x. We don't have a definite form for continuous variable. Now let's proceed with the first example. Okay, this is a first example for the discrete probability. Suppose the equation y is equal to 20 plus 100 of x converts a PSAT math score x into an SAT math score y. Suppose the average PSAT math score is 48. What is the average SAT math score? So we are given with the following. Okay, the equation that converts PSAT math score as y is equal to 20 plus 100 of x with a population mean at x is equal to 48. So we are required to solve for the average SAT math score. When we say average, we're going to deal it with mean population. So mu of A plus B of x, okay, is equal to A plus B multiplied with the mu or the mean population at x. Okay, the solution proceeds with the mean population of the given equation, 20 plus 100 of x is equal to 20 plus 100 multiplied with the mean population at 48 score. So substituting now the following values, this gives us a 500 answer. The second one, suppose the equation y is equal to 20 plus 100 of x converts a PSAT math score x into an SAT math score of y. Suppose the standard deviation of the PSAT math score is 1.5 points. What is the standard deviation for the SAT math score? So we are given with the following. The equation again at y is equal to 20 plus 100 of x, whereas the standard deviation is at 1.5. If we're going to solve now for the required, which is the standard deviation of 20 plus 100 of x. If we're going now to proceed with our solution, we have to square the variance, okay? I mean the standard deviation at x is equal to 1.5. Okay, this gives us 150. And then 2.25. Okay, solving now for the variance. Variance now is equal to 100 squared, multiply it with variance at x. Okay, so 100 squared multiplied with 2.25, this gives us 22,500. For the next problem, we're going to tackle this on our next video.